So one concept that we've spent quite a bit of time discussing recently is the inclined plane problem. And so that's where you have an inclined plane like this, or a gradient as it's sometimes called, with an angle theta. And generally, as we've been looking at, you'll have a mass m. And so in the previous video, we talked about how we can understand the acceleration, or really model the movement of this mass when there's no friction. However, in this example, we're going to take a look at friction and see how friction works and how it would affect this. So first, let's just take a look at friction in general. And let's say we have a plane, and we just generally have a mass on it. We'll just say that this plane is, flat, but it's slightly rough. And so you'll hear generally two sorts of words. If you hear frictionless, or smooth, or perfectly smooth. This generally indicates that you have zero friction. Otherwise, if you hear something like consider friction or rough surface, if you hear rough, that's a perfect indication that you will have to use friction in your work. And so when you are defining friction, what they'll generally give you something is called the friction coefficient. And this is how you determine friction, actually. Because think about it. If you have I'm just going to say coefficient, CE. Because if you think about it, some surfaces are going to be more rough than others, and thus they'll provide more friction. For example, imagine a carpet. If this was a carpet, it might be really hard to move this mass m across. More difficult than it might be to move, for example, this mass across a wood surface or an ice surface. So usually you don't have to remember these, or you'll have a lookup table. So the coefficient of friction will be kinetic friction, and it's denoted with this Greek symbol here, which is pronounced mu, just like you can remember as a moo of a cow. And it's essentially a U that has a few curls at the end, and it comes up, and maybe on your sheet you might see it a little bit straighter, like that. But these are all mu's. And when we have this K at the end, like I have here, mu sub K, this K stands for kinetic friction, or just rather kinetic. And kinetic means essentially moving. So when you see this means that the coefficient of moving or kinetic friction is going to be this, mu sub K. And so this will generally be a number, maybe a decimal, and let's say it's just 0.1. And it has no units. There's no units to it. It's just a number. And it'll be written like this, mu sub K. You may also see mu sub S, and this is mu sub static. And we'll talk more about this in a later video, but this is for static friction. And static friction and kinetic friction are very different. So let's go over the quick differences between them before we move on. Static is, as the name suggests, when things are not moving. So, for example, if this mass m here, down here, is at rest, right now it's at rest, and you try to get it to move, there's going to be a certain amount of static friction needed that you'll need to overcome in order to get it to start moving. Versus if you already have something that's in motion, then that's a completely separate value, only somewhat related, and this is for when it's moving. So once you've overcome static friction to get this mass moving, then only kinetic friction will be acting on the object. So let's move on from there. And let's talk about how do we use this mu sub K. that we're getting, right? We have, as we were talking about, mu sub k, that's the coefficient of static friction. I'll just write it once again here, mu sub k. And in this example, it's 0.1. And often this number is really just representing the proportion of friction that will be between these two surfaces. And this is dependent on the two surfaces. So dependent on, I'll just write dependent dp on two surfaces. And maybe if there's 3 surfaces or 4 surfaces, actually it can be 2 plus surfaces, right? Because if this mass contains multiple surfaces in it, maybe half of it is wood, maybe this half is wood, and then the other half is maybe ice, then this will have its own specific coefficient of friction. But it is not dependent on mass. Not dependent on mass. And this isn't to say that kinetic friction isn't, as a force, isn't dependent on mass, but rather it's to say that the coefficient of friction is not dependent on mass. Once we use this coefficient of friction, we'll incorporate mass into how we use it. So how do we use coefficient of friction, mu sub k? We've talked a lot about it, but we haven't talked about how it's actually used. So for this example, mu sub k, or the force of friction acting on an object, is going to be proportional, and usually they write this alpha for proportional to the normal force acting on an object. So let's talk about that. When you have a force of friction, especially force of kinetic friction, it's going to be opposing the direction of motion. So let's say, for example, I'll just draw a nice pink arrow up here to show that this is moving this way, this block. Well, friction will be a force, and it can really be drawn as a force. I'll draw all my forces in yellow. It can really be drawn as a force directly on the center of mass that's going in the opposite direction to motion. And we generally call force of friction, it can be called a lot of things. In this case, we're just going to call F sub F for force of friction. Now, there can be many other forces acting on this. However, the force of friction is only dependent on the normal force. It's not dependent on the other, on the speed of how fast it's moving. It's not dependent on, it doesn't change over time, assuming that this mass isn't changing and this ground is both staying the same material. And it's not dependent on the other forces that are acting on it. Let's say there's a huge pushing force making this go this way. Let's say this is a pushing force, so we'll call this F sub P. Maybe there's a human behind here who's giving it a push in this direction. This force at all is not going to affect the direction this way. So what is affecting the direction this way? Well, it is the normal force. And remember, the normal force is equal to the weight. The weight is mg. And so the normal force comes right back at it from the ground. This isn't usually the position you would put it in, but I just want to show you. And this is F normal. And remember, F normal is just going to be equal to, at least in this case, mg. And so what this is saying is that the more weight you have of an object, as weight increases, the normal force is also going to increase. As well as if the mass of this increases, the normal force is going to increase. And that makes sense. If you put a small little object on a carpet, it's not going to be too hard to move because there isn't a lot of friction. However, you place a couch, there's going to be a lot of friction, making it much, much more difficult to move. So, including the fact that the couch is also very heavy. So how do we calculate this? Well, I said it's proportional to the normal force, and so when something's proportional to another force, first, let's rewrite this. This is essentially to say, I'm going to bring that up here. Sorry about that. This is essentially to say that the force of friction is going to be proportional to the normal force, and the normal force is just mg. And whenever you have a force of friction, or whenever you have something that's proportional to something else, there has to be a constant of proportionality. And so this is essentially saying that, and be it, weirdly enough, the constant of proportionality is just mu sub k. So the force of friction on an object is equal to mu sub k times the normal force acting on that object and the surface, which in this case is just mu sub k mg. So there we go. That's the force. And this really, actually, I should denote this. If f sub f was a vector, this would really just be the magnitude of the force. This is not the direction of it. The direction is opposing motion. And so I'll add that. Opposing motion. Opposing motion. And that's a really key idea. The force of friction is never going to help something move along faster or with higher acceleration. It's always going to slow something down. So that's really important to remember. So now that we have all this in mind, let's try to consider the following example. Before we get onto inclined planes, let's just consider a flat plane example. So we'll draw ourselves a nice flat plane. Just here, we're going to have ourselves a mass of m, and we're going to, remember, this is going to be m. We need to draw our forces in. We have a force, I'm going to call this force Fp, because this is the pushing force. It's going to be 10 newtons. The mass of this object is going to be 10 kilograms. We're going to have, or you know what, I'll make it 5 kilograms. 5 kilograms. We're going to have gravity equal to, not 9.8, but 10 meters per second squared. And the question is, and also we're going to have a mu sub k. This problem is going to involve a friction, kinetic friction, and that's going to be 0.1, just to make things easy. So now the question is, what is the acceleration of this object on this surface with all of these things in mind? Well, it's always important to first draw a free body diagram. We already have part of our free body diagram drawn. We have the force of the person pushing in this direction. In the exact opposite direction, opposing motion, we're going to have the force of friction, which is something we'll have to calculate. And we're going to have the weight, mg, which is coming this way. And also, that's going to be the normal force, which is going up. And so if we remember, the force of friction is always mu sub k times the normal force, which in this example is mu sub k times mg. In this example, if we bring this in, let me do this in a different color. If we bring this in, that gets us 0.1 mg. So that's the force of friction. And let's just save that up here so we don't forget it. Force of friction is going to be 0.1 mg. Newtons. And this should really be newtons, but we don't need to write that because mass and gravity already have dimensions to them. So then we have essentially all the forces we need to see how it's moving in this direction. And it's always important to draw the arrow of what direction it's going to be moving in, and I'll draw that in pink. So let's try to discover the acceleration of this object. We have all the forces we need, and we know that F net equals ma. From Newton's first law, we know that F net is going to be this 10 newtons from the force that's pushing on it minus, this is really important, the force of friction. Because remember, the force of friction is going in a different direction. And it may even be better to say plus negative 0.1 mg. Because really, this is going in that direction. And so this gets us, if we solve everything out, we're going to get times 0.1, and then mg is going to be 5 times 10, which is 50 newtons. And then we'll take, so we have our 10 newtons here, and then this will then come out to 10 newtons minus 5 newtons. This gives us a total net force on this object of 5 newtons, including friction. And so then if we divide by the mass, so we'll remember we have F net equals ma. Currently this is 5 newtons acting on this object. We divide both sides by m, which is, remember, 5, and we get that the acceleration is going to be exactly 1 meter per second squared, including friction. So that's great to know. Let's just compare that with what we'd expect the acceleration to be if we had not had any sort of friction on this object, and we could assume it'd be this 10 newtons equals ma. We divide by mass, and it would be 2 meters per second squared if we had not considered friction. So that makes perfect sense. Friction is slowing down this system. Okay, so now that we've introduced this idea of friction on a pretty deep level, or of kinetic friction rather, let's consider that in the context of an inclined plane. So we have our inclined plane here, and let's just complete that. We have our box up here, or it should just be mass, not a box. And we're going to have an angle of theta on this. And we're going to give mu sub k, this should extend a bit further down, we're going to say that's 0.1 for all purposes and intents. And this is m. And so if you remember from what we learned previously in the last lecture, was that the component, if we draw these forces, which is specifically just going to be mg going straight down, there's going to be a component of mg that goes parallel to the inclined plane, which is going to push it down. And if you remember, this is mg sine theta. And there's also going to be a force this way. And this force is going to be, yes, you guessed it, mg cosine theta. If you don't see how this is mg cosine theta, you should watch the last video just to get some background, and then try to see if you can figure out why it's mg cosine theta yourself. It's a pretty natural extension to the way we determine this is mg sine theta. And so I think you guys will be able to get it super easily. Just make sure you completely understand the last video. And so this force here, mg cosine theta, well, this is the normal force. It is exactly the normal force. Because remember, the normal force is the force that's perpendicular to the surface. So the surface is slanted, and thus the normal force will also have to be slanted. So this gives us an F normal of mg cosine theta. Mg cosine theta. That's lovely. And we have this mg sine theta, and that's yes. And we actually almost forgot to draw in one of the most important forces for what we're talking about today, which is this is friction. Friction, remember, is going to be opposing the direction of motion. So that's friction F. And I'll draw in pink the direction of motion again. That's how motion is going. So let's see if we can figure this out. We'll again use Newton's second law, which is, we're trying to find the acceleration, just to clarify. What is the acceleration? Find that. And again, we can use Newton's second law to do that. We'll always start out with F net equals ma. And what is F net? Well, it is the sum of all the forces on this object. We have a force, assuming we make this axis here. Let me just show you what I'm talking about. If we were to make trying to find a nice color to do this in so it doesn't confuse anyone. I will do it in this green color, I guess. So if we look at this as the axis that we're discussing the forces on, this is actually the best axis to discuss the forces, because all of the forces that we want to discuss that are affecting the movement of this object are all on this plane here. Are all parallel to this line. So by doing this, it really saves us all the trouble, and instead of having to worry about directions and vectors, we can just subtract and add to determine the direction, to show direction. And so in the positive direction, we'll make sliding down the positive direction. So we have a force mg sine theta, and I'll actually do this in a nice yellow color to match. Mg sine theta. And then we have our friction, force of friction. And remember, force of friction is equal to mu sub k times the normal force. And we know that this is thus mu sub k, and we know the normal force is mg cosine theta. Mg cosine theta. And so and this is going in the opposite direction. Remember, this is the positive direction, and this is the negative direction. So we'll have to subtract off from our forces, because it's going in the opposite direction, this force of friction. So that goes here as mu sub k mg cosine theta. And there we go. Those are all the forces that are acting on this mass here in this plane, or in this direction that we're seeing here, that are affecting movement. And so from there, we can solve for acceleration. When we solve for acceleration, we'll get the following. We get that A equals mg sine theta minus, I'm going to keep it all in one color just because we now know that this is really one cohesive understanding of how this object is moving. We're going to divide that by mass, and we're going to apply some cancellation. That goes away, that goes away, that goes away. And again, something that you'll probably find quite interesting is that the mass of an object does not really affect acceleration, just as we saw previously in the last video, but even in this video, even when we consider friction, kinetic friction. That's mu sub k g cosine theta. And there we go. That's the formula if we want to calculate the acceleration of this object down this slope, considering friction with a coefficient of mu sub k. And you know what? We have mu sub k up here defined as 0.1, so really this could be plugged in as 0.1. But it really doesn't matter because it represents the same quantity. And chances are when you do your problem, it's not going to be 0.1. It may be something smaller or slightly bigger. If we do some quick analysis on mu sub k can never be equal, or mu sub k rather, always has to be less than 1. And that's just something to think about, or less than or equal to 1. And it has to be greater than 0. Because friction, if mu sub k, for example, was a negative number, it would make the friction force go in the direction of movement, which is not how friction works at all. So with all of that, feel free to comment if you have any questions or realizations, and I'll see you back later for more physics videos.